QuantSpeak, expert insights from Quants for Quants.
Welcome to QuantSpeak, a new podcast from the CQF Institute at Fitch Learning.
Hi, I'm Dan Tudball, editor of Wilmot Magazine. They said it couldn't be done, yet here we are, the second episode of QuantSpeak. Deep learning, a subset of machine learning methods based on artificial neural networks with representation learning, has been generating some excitement in the finance space over the last year or so, with a fast-growing body of research and increasing coverage at conferences. So, how is a quant to engage with these artificial neural networks that are inspired by the way biological brains process information via distributed nodes? Today, we'll be talking about just that topic with Tim Wood, Senior Solution Architect at NVIDIA, and John Ashley, NVIDIA's General Manager for Financial Services and Technology. NVIDIA is a name that has been closely associated with deep learning since what might be called its Big Bang moment back in 2009. Tim's talk, the CQF Institute, Deep Learning for Derivatives Pricing from Theory to Practice, suggests this novel approach to pricing is on the verge of breaking through to the mainstream. So let's get into it. Hi, Tim. Hi, John.
Hello, good afternoon, good morning, depending on where you are.
Good morning from sunny, almost California.
Thanks very much both for joining me. So I'll put the first question over to Tim and John, if you want to jump in. Tim, can you put deep learning in the wider context of machine learning? Because machine learning is something that seems to be, almost everywhere at the moment. It's got huge coverage across media and in terms of finance, in terms of the conferences. So machine learning seems to be something that has reached a level of maturity almost in the consciousness, at least, of financial services practitioners. Could you put things in that context for us as to how deep learning as a subset grows out of that or relates to machine learning as we generally understand it in the finance context?
Yeah, sure. I'll give it a try. So I think in your introduction, you've characterized deep learning as a subset of machine learning, or I would go further and say artificial intelligence. Deep learning specifically refers to artificial neural networks, and that's a bit where the term or the deep part comes from. And so it means very large neural networks, so many hidden layers, many neurons on each layer. And the reason why deep learning has sort of come to prominence in the last, let's say, coming on for 10 years, and in particular driven by NVIDIA technology, is two things. So it's driven by an abundance of data and an abundance of relatively cheap and available compute, which makes because the two things that you need for deep learning to be effective are lots and lots of data for training your models, and lots of compute for those models to be trained in a reasonable amount of time. And the GPU architecture, so NVIDIA GPUs, are born out of 3D graphics acceleration. Later, they became, through research and development in industry and academia, they were applied to HPC. And so in the financial services industry, they've already been deployed very broadly for HPC, for derivatives and risk type applications. And researchers began to realize that this architecture was also extremely well suited for training of neural networks. And because of the vast amount of compute, parallel compute available in the GPU architecture, able to train very, very large networks. Where then does this fit in financial services industry? Because of course, already there's been a lot of machine learning used in the financial services, across the financial services. So we can think about within banking, from retail applications, looking at customer behavior, across to more on the trading side. So, identifying patterns, executing strategies. and the proprietary trading space or in the investment banking space, and indeed my own talk, which will focus more on the pricing of derivatives and calculation of sensitivities and so on. What does deep learning do that other machine learning techniques can't? Do you want to jump in, John?
One of the things that sets deep learning apart from other machine learning techniques is it's proven to be adaptable to non-tabular data. So unlike most other machine learning techniques, you can apply deep learning to text. You can apply it to audio. You can apply it to video and images. And so that has opened up a set of opportunities to apply AI, machine learning, deep learning, whatever moniker you want to attach to it, to apply it to a lot of use cases that other machine learning techniques are either hard, almost impossible, or completely impossible to apply it to. I think even in the realm of sort of structured tabular data, deep learning gives you a way to use models with many, many more parameters that are nonlinear, and still, with enough work, not manage to overfit everything to a ridiculous extent. So even in the tabular space, you can find more interesting nonlinear patterns using these neural net-based approaches than you can with many of the sort of standard machine learning approaches that really tend to carve space up into more linear chunks. Maybe a little theoretical, but that's the big difference I see. It opens up a whole set of non-linear use cases in the tabular space and a complete revolution in the unstructured data side of things.
Thanks, John. The opportunity to look at more complex correlations, is that an aspect of deep learning that that really should be at the forefront when people are thinking about this application in terms of finance? Because as you said, it's very well suited to non-tabular data. We're all about correlations when it comes to derivatives pricing and risk management. So could you guys go back a little bit, because it would be good to get a view on this sort of multi-layered aspect of deep learning, you know, where you start with, where you're able to, you start with specific categories, I guess, and you're able to build up from different layers of information about a specific target. In terms of image recognition, for example, there are different parameters, as you said. Is that correct, my understanding of it?
I think I was thinking about your question about, or your remark about correlations. So in the work I've been doing, which I'll be talking about in a couple of weeks, I've also tried to explore what are the limits of what's possible using deep learning in this particular pricing space. And I'll be honest with you, so I haven't really thought about either searching for or modeling correlations, but one of the conclusions that I'm coming to is that if you can decompose a pricing problem into its components, so you can think about, you know, optionality or early exercise because of some market event simulated or otherwise, a default event, and then compose them back together, then I don't see why the modeling of correlations shouldn't then also be tractable in the context of deep learning. Although I would hesitate to sit here now and give you a recipe for exactly how to do it. one of my emerging conclusions is that the limits to what you can do with deep learning to some degree, it's the limits of what can you imagine, and then work backwards from there. Can you then reduce the problem space to some set of observables or some set of data that you either can obtain or can generate? It's a problem of expressing the problem in a way that's tractable. And tractable then means, data, and do you have the compute? And of course, that's the part where NVIDIA steps in, because of course, as you start to scale your problem, the volume of compute you need is typically growing exponentially. And so perhaps the other limitation on what you can do, apart from can you think of how to formulate your problem, is also, can you then solve your problem in a reasonable amount of time given the resources, computational resources? Of course, the availability of computational resources is growing and growing all the time, which in turn is feeding this rapid development of deep learning models.
Maybe I can add in, going back to your most recent question, Dan. If you look at these deep learning, these neural net systems, one of the things that really allowed them to revolutionize image processing is the fact that they can discover their own primitive patterns, and then they can start to assemble these primitive patterns at the higher level structures. And so instead of, right, in the image processing space, for instance, it's easy to explain in that space, maybe not as easy in the tabular data space. Early layers of the neural network end up reproducing interesting things like edge detectors. It took computer scientists a long time to come up with effective edge detectors, but neural networks can rapidly learn that that's an efficient way to organize the early layers. And then if you're training it to recognize faces, somewhere in the early to middle part of the network, features start to emerge that are tracking things like eyes, right? They're starting to learn how to put these edge detectors and these things in to understand eyes. And then somewhere even deeper in the network, it's starting to understand that a typical face, there's a relationship between where an eye and a nose are. And if you think about that in the structured data space, you can almost think about it as saying, hey, if you imagine building up my signal, analyzing my patterns, say with a Fourier analysis or a wavelet kind of thing, right? Where you're saying, hey, I've got some signal, it's a summary, a sum of a bunch of patterns plus a bunch of noise. The difference with deep learning is the neural network can figure out the primitive patterns and how to assemble them. Whereas with a lot of other techniques, we have to provide a library of primitive patterns as an expert. We have to define all that. And then we have to manage the search space to figure out how to put it all together. And the neural network can both determine those primitives and determine how to assemble them, as long as you give it enough data and compute.
Thanks, John. Yeah, that makes sense. And that, I mean, I think at that point, it kind of provides a useful segue for Tim to perhaps talk about how, because it's this multi-layered aspect of things.
That was my clever plan.
Yes, it's all coming together, Tim. It's over to you. So, how does that fit in with what you're going to be presenting at the talk?
Well, so what I'll be presenting at the talk, deep learning for derivatives pricing from theory to practice. So my target audience is people who've come across, the various papers. There's a lot of conference talks at the moment about this topic, but maybe there's a bit of a gap between specific cases in the papers and actually getting up and running, getting practical. So what I'll be showing is a bunch of quite toy cases, but an experimental framework that I've developed so that to actually begin training models, to begin analyzing what is the performance coming out, and the types of levers that you can pull and adjust to change or improve the behavior of the outcomes. And so the goal of the talk is to sort of demystify for the audience, how do you get from reading a paper to actually doing it yourself? And so by the end of the talk, I hope that people will be able to, go away thinking, okay, now, something that was abstract to me before is now concrete. Now I know the tools that I need, on my laptop, in my enterprise, in order to actually begin experimenting with this and using this methodology. I think along the way, I will also explain, why it's relevant, because I think, a question that, arises is why another methodology? There are already, quite a few out there. Prior to joining NVIDIA, I spent some years working as a quant. Later, I had responsibility for a risk system in a bank. So I have sort of quite a broad view on, first of all, methodology, and then also the practical aspects of implementation in, to a working solution. Now, when I joined NVIDIA, there's a very strong emphasis on artificial intelligence. That has been for many years. And this was also when I, first became exposed to the notion of, using these methodologies for derivatives pricing, which is, my old field in my previous job. And working at NVIDIA brought me into contact with a lot of practitioners. So, we speak with quants and practitioners from many different organizations. And I noticed, so a curious pattern began to emerge where there would be sort of two sets of people: those that didn't really believe that this methodology would ever work, sort of quite negative. And then a sort of more data scientist type profile that was very positive on it, said you can do everything with it. And this kind of was curious to me. And so that's what led me to investigating this topic further and to try and, demystify it. And so in large part, that's what this talk is about, is sort of, first of all, that journey of finding out what is possible, and then from first perhaps confirming that this is a methodology that's applicable in this field, to then beginning to do something practical, and then trying to show others the way in order to do that as well.
It's an interesting scenario that you're describing there, Tim, because the whole, this bifurcation between the sort of naysayers and the more sort of data science friendly types kind of describes the evolution of the definition of what a quant is over the last 20 years. Actually, I mean, you were at the bank for some time before going over to NVIDIA. And the interesting thing is that I remember when machine learning was kicking off, there are a lot of people are saying, well, what's the point? We've got PDEs already. It's just doing the same thing again. What's the point? It's nothing new, and those were the naysayers. But people who are aware of what was happening in other industries, particularly e-commerce and so on at that point, was saying, look, the quantities of data that you're going to have to deal with, it isn't necessarily something to be wary of or scared about. This is a matter of adding some tools to the arsenal, but attacking the problem that has always existed.
Well, I think, you see, that's a crucial point, Dan. It's and I wonder whether this, bifurcation, as you characterize it, it is perhaps a sort of, a resistance to change, which is quite a human characteristic. But your remark about, this is another tool in the arsenal, I think is really hitting the nail on the head. So, if we sort of, narrow in on the topic of the talk, by discussing deep learning in the context of derivatives pricing, we're not talking about taking the existing tool set and throwing it out of the window. It's really an extension of what is already there. And then this is a perfect moment to talk about the operational considerations. So what is the promise? Why do it anyway? So the promise, if we just take a little step back, and when we talk about deep learning, when we talk about using artificial neural networks in general, there are two things we're going to do. We first train the model, and then we deploy the model. There's a stage called inferencing, where we feed it new data to get a new answer based on that new data. So we can think about a new derivative, and we want to get a valuation and sensitivities out of it. Inferencing is extremely fast indeed. And so the operational benefit of this methodology is, if today you have a not even particularly exotic contract that you need to value, there's a good chance that you'll be leveraging numerical methods, Monte Carlo simulation, which means that each valuation of that contract is going to be taking, seconds and potentially many seconds. Now, if you could turn that time from many seconds into a fraction of a second, you've just gained an operational advantage, because your overnight, potentially your pre-deal, but certainly your overnight risk batch is going to be completing orders of magnitude quicker than it does presently. That's good. You can run your risk batch more frequently. Another view on it, the real world is messy. So occasionally your overnight batch is going to break, wonky market data, bad trade data. You get to the morning, go, oh dear, now I need to rerun the batch. Yeah, but you need to report in 2 hours. If you can run the whole batch in 5 minutes, then you're in a very nice place. So from an operational standpoint, it has the potential to give a real operational advantage. In terms of tools, and you mentioned validation. So this was something that I was thinking about when I first started approaching this topic. I was like, well, again, the real world, it can be difficult. So you can have something running, in a sort of laboratory environment, but that's the fun part. The road to production can be long and arduous, and indeed validation, internal and external model validation it can be a very long and drawn out process, very difficult process, and for good reasons. But indeed, the application of deep learning, as I've been looking at it, is not throwing out the rule book or throwing out the toolbox that we already have. It's just an extension. So if you have a model implemented for pricing a particular asset class or particular type of contract, you don't throw that model away, but you use that model to train your deep learning, your neural network, so that you can then solve for that model more quickly. And in that sense, deep learning can in some ways be viewed as a numerical method next to Monte Carlo or next to finite difference schemes. I wonder if John would like to add anything to that, but this is kind of where my thinking on this is.
All right, so there's a perception that deploying GPUs requires a lot of upfront coding and preparation and so on. What can you say about that?
In the context of machine learning, almost nothing could be further from the truth. So if you're doing deep learning, so my advice would be, if you're going to do deep learning, start with a framework. Don't start with writing a neural network, because that's already been done for you. It might be that one day down the road, you might want to have some kind of tweaks, etc., and that's fine. But in the first instance, take an off-the-shelf framework. So there are many out there. I think the most widely used I see in FSI are TensorFlow and PyTorch. I have no preference, but these seem to be the most commonly used. You can download this from the internet. If you want to run it on GPUs, you can take a containerized version from NVIDIA, from the NVIDIA GPU cloud, or we call it NGC. Provided you have a host with a GPU, the NVIDIA driver, and you are able to run Docker containers. Not sure if I should even say Docker containers, but certainly a container. pull the container, the PyTorch, for example, container from us, and you can begin using PyTorch. You use PyTorch as you would use it if you were running on CPUs or some other platform. So the effort to accelerate your deep learning workloads on NVIDIA GPUs is exactly that. It is as much as downloading a container from the internet and starting it. It's GPU acceleration for free. This in the AI space. This is where it is. I think if I can speak to the perception which you refer to, Dan, this would be probably a reference to the transcoding of existing model implementation. So then we're not so much talking about artificial intelligence and deep learning, where you can leverage, an out-of-the-box framework, but you would like to accelerate existing proprietary code, or perhaps you'd like to replicate the functionality of proprietary code or third-party code. The effort can be considerable, but I think everybody starts from a different point. If you have internal implementations, then it's possible that you may be able to scissor out parts of the code, but it's likely that you will be writing CUDA or C++ for CUDA, which is the high-level programming language for programming an NVIDIA GPU directly. But even then, I would say, compared with more than 10 years ago when I started my career doing this sort of thing, the availability of libraries and the richness of the tooling, the development environments, in order to be productive in writing and testing and maintaining CUDA code or CUDA C++ code has improved drastically over the years. So in fact, the part of NVIDIA's strategy for CUDA is that end users, that developers shouldn't have to write any CUDA code at all. And in support of this, NVIDIA's recently released the HPC SDK, which is a collection of compilers that allow you to target multiple architectures using, in this case, I'm talking about C++. So you would write standards compliant C++ 17 or later, leveraging the parallel components of the standard template library. So there you have regular containers, which are already implemented as parallel containers and parallel algorithms, which allow you then, to using the compilers bundled with the HPC SDK, target different architectures, including the NVIDIA GPU, so that regular C++ will be accelerated out of the box on the NVIDIA GPU without needing to write any CUDA code at all.
Now, I had a follow-up there. I mean, what you were referring to was there's the importance of the community that's built up around CUDA over the last 10, 12 years. And every community has its history. So this is my rambly segue to this. Last week, a new book published, Genius Makers, the Mavericks Who Brought AI to Google, Facebook, and the World, by Cade Metz. Anyway, I read an extract of this book in Wired, and it's talking about Professor Jeff Hinton auctioning his neural network technology in a hotel in Tahoe in 2012. And basically the gist of it is that this was essentially the beginning of the Big Bang in deep learning. But we know something slightly different. We know that in 2009, Andrew Ng was at Stanford University, was using NVIDIA GPUs to really kick off what was the Big Bang in deep learning. So I was just wondering whether you or John had a comment on this. Well, it's just this book came out really, and it seems to place the beginning of things are a little later than I understand it to actually have kicked off, certainly with NVIDIA.
So the history of AI neural networks on GPUs specifically is tied up with the history of the development of deep learning, as we call it now. And I think there is no real one point that says this is where we went from, multi-layer perceptrons to deep learning. It wasn't, there was no single point that was the turning point. There were people doing work, and I think a lot of those people can make justifiable claims on having been the first to do this or having kicked off that. I think the point that it moved from a very academic theoretical exercise, right? The overnight success moment, right? Just like the hardworking band that's been out touring for 10 years and everyone in it's been playing instruments for 20, and suddenly they have their big hit. They just burst on the scene and it looks like they came from nothing. There was a lot of work that happened before these moments. And I think it all finally came together and became very much part of the public awareness with the ImageNet win, right, with AlexNet in 2012. But there was a lot of development, a lot of theory, a lot of compute, a lot of imagination, blood, sweat, tears, grad student hours that went into creating that overnight success moment.
Thanks, John. I've been reading a bit about adversarial approaches to machine learning. How does deep learning fit in with artificial neural networks in terms of, say, adversarial approaches to machine learning? So you're kind of like pitting a sort of a initial model against sort of a I don't know, like an auditing type algorithm, and they're kind of battling it out. That's the impression that I get. Is there anything to say about that in terms of deep learning?
So I think there's two sides to this. Let me take a stab at this one. So there are two sort of adversarial ways that people talk about adversarial models in the deep learning space. One is sort of in adversarial examples, right? So and the common example people give is, hey, can I put a sticker on a stop sign so that an autonomously driving car won't recognize it as a stop sign, right? And there's an adversarial process there where some bad actor is trying to confuse a neural network by presenting data that's not within its sort of trained repertoire. The other side of that says, hey, let's take that kind of concept, but let's use it to our advantage. And that's where it fits into generative adversarial networks, or GANs. And GANs are a way that a lot of people are looking at to augment data sets. You take one neural network and it generates, and again, we'll use the image example because it's just easier. It generates a picture. And another neural network gets a real picture of a tree and this generated picture of a tree and tries to tell which is which. And if you train them carefully, eventually the generator learns to produce very photorealistic trees. And the discriminator gets really good, that the other piece of that network gets really good at telling real from fake trees apart. And so that's using this adversarial approach to generate, to build a generator of impressive fake photorealistic trees. And if you, instead of generating trees, if you try and generate, say, examples of credit card fraud, because this is a very rare case, right? Most transactions are legitimate. If you want to train any machine learning model, including deep learning models, having a bigger variety of fraud data would be useful. And so you can train a GAN to generate fake fraud. which you can then use to help supplement the training of models. So I think there's adversarial gets used two ways. One in that sort of bad actor trying to confuse a neural network way, and another that says, hey, let's take that thought and use it in a positive way to build a photorealistic or a data realistic generator of information.
Just picking up from that, there's a growing body of work around using GANs for generating market data. So I think that the methodology is often referred to, as market generators, and they can be used in different ways. I think the most examples I've seen, they are more for strategy back testing, but I've actually also seen there's a paper I saw recently, which is about generating volatility surfaces, specifically rough volatility surfaces. I understand rough volatilities are very much in vogue at the moment. And so it was interesting to see this sort of emerging method, or let's say this quite fashionable technique for modeling volatility combined with deep learning. I'm not so sure about its concrete application in industry yet, but certainly GANs and this sort of generative deep learning is one of the I'd really go as far as to say one of the key use cases or key examples of deep learning in specifically in the sort of investment banking or trading space.
Thanks, Tim. Thanks. No, I think that's great. So I've got to wrap up with a slightly more whimsical question, because theoretically it would be entirely possible, if we extend it into the future, it would be possible for a neural network to be able to learn how to replicate consciousness. Would it be possible that we might be living in a computer simulation and we are in fact all just something like the Matrix?
If we are in a simulation, I really want to meet the programmer and take him out back behind the woodshed.
Yeah, your question reminds me of the holographic universe theory, where there's a very, unfortunately I couldn't find his name quickly enough, but there's a very renowned physicist who I've seen his lecture once, where he gives quite a convincing argument that actually we're all living in a hologram. Is that hologram being driven by NVIDIA? Maybe.
Well, curious minds need to know. So I think that's good. I was either going to go with that or a Star Wars, Star Trek question. I figured the computer simulation one would be more fun. Is there anything that either of you would like to add, take the opportunity to add, going out to our particular audience of quant finance practitioners, with regard to research and development, or the way in which you feel things are going to progress with regard to deep learning techniques? How far off are we to a sort of adoption, I guess?
That's a good question. One of the things I sort of noticed as I sort of look at this topic again more recently is that it's not a question of if, but a question of when. And I think we're actually already transitioning it into it. So, more than a year ago, it was quite difficult. I found it quite difficult to find concrete examples where either a bank would tell me, yes, we're doing it, or it would be in the news. In the last 12 months, that has changed. And I also believe that the number of conference talks and the number of papers being published, the quantity is up and it's accelerating. So this is a methodology that is arriving or has arrived, and will become more and more widespread. And I think that's equally true outside of the financial services industry. That our CEO Jensen Huang is always saying that artificial intelligence is going to impact every industry, and I believe that to a lesser or greater degree is absolutely true. It is going to have an impact everywhere, and it's inescapable. I think the question is, how quickly and to what degree.
Great, thanks, Tim. John, do you have anything to add to that?
Today, there are traders and quants all over the spectrum, right? There are people whose trading strategy is formed by reading a bunch of newspapers, and a guy puts his feet up on the desk and then makes some decisions, and that's how they trade. And there will still be people doing that. But the thought of at the more advanced firms today, no one would trade without massive compute, right? No one would trade without massive data crunching. And I think that's just going to become more and more common, because even if you're a discretionary trader, if you are augmented by a team of AI-powered assistants who can read more languages than you read, prioritize more news feeds than you could ever look at for you, and then be part of a feedback loop where you're continually teaching them, that was a good recommendation, that was useful to me, no, you got that wrong, right? Even in the discretionary trading side, I think AI assistants are coming. They're already here for the most advanced firms, they're coming everywhere else. On the algo side, I think Tim's touched on data generation for backtesting algos is going to be touched by AI. Derivative pricing is going to be touched by AI. Looking for patterns in data that you can turn into tradable insights, touched by AI. Reading news, right? Understanding news feeds, understanding documents and regulatory filings and what all that means, and synthesizing this deep data for an algo to consume, touched by AI. It's already here in places and parts, and it's a trend that's going to accelerate.
Thanks again both for your time.
Thank you for listening to QuantSpeak. Don't forget to subscribe, and do sign up to the CQF Institute for more insights into quant finance.